From the beautiful studios of Sway Happy, this is 1/6 graphical transformations. One of my favorite topics, I would have to say, in graphing. Really, you know the parent functions, you got them all down, and now the fun begins where you have to learn which way you're going to translate them. Translating just means sliding them left and right or up and down, or stretching them horizontally or vertically, or compressing them or flipping them. And the big key here is to always remember, just like a good exercise class, that you always stretch before you slide, right? So you always stretch before you slide. So take care of stretches first and then do your sliding. So again, stretches are compressions, stretches, and reflections, and slides are your left and right and up and down translations. All right. The other big rule about this is if it's inside with the x, you usually do the opposite or you do something weird. So if they're multiplying a number inside with the x or something's inside with the x, something weird is happening, do the opposite. If it's on the outside, it's happening to the y's, and you just do what it says. And I'm probably going to use like an absolute value graph or something just to explain this as we go along. So let's talk about our friend y equals absolute value of x, right? We know that that's just a graph, boom, like this. Beautiful graph, y equals absolute value of x. Now let's do some stuff. So the first thing you want to do is we're going to start off probably here with some stretches. So these are, some slides. We're going to start off with our slides. So this first one, if they add something to the x inside the parentheses, or in our case inside the absolute value, like I would have something like y equals the absolute value of x plus 2. So they did something on the inside. That's going to tell you that we are doing a stretch, a slide, and we're moving it left that many units. So this would imply left c units. So on my example there, this graph would be moved left 2 units, and I know that because it's inside with the x. So inside, when you add or subtract to the x, you're going to move the graph left or right, in this case left, and it's going to be that many units. So every point on the original graph, so this is going to be my original graph up there, every point that was on there, you could just take your little table of values and you could literally just go left 2 units. So you could just subtract 2 from each of the x's, plot that exact same y, and you would have a perfect graph. So that's what I mean by the inside is the opposites. When you look inside and you see inside my absolute value bars, there was a plus 2. That meant left 2. Very bizarre, right? Let's talk about it if it was the opposite, right? Look right down here. We got this translation that is minus c. So what does that mean? That means we're going to go right c units. And so what could I do there? Well, I could have y equals the absolute value of x minus 5. And then I see that minus 5, I see it's happening inside with the x, so that tells me it's a left and right because it's added or subtracted, and it's the opposite, so that means it's going to go right 5. And really what you could do is take any point on the original parent function, and you could just take it, and you could add 5 to each of the x's. And if you did that, you would have a beautiful translated graph, and it would be right 5. All right, what about the weirdness then? What if we have something added to the outside? So notice in there it was with the x. Now we're doing the function, and then we're going to add something to the back. Well, that would move your graph up d units. And notice not opposite because it wasn't inside with the x. What would it look like on our graph? It'd be like y equals, and I'll use the 2 again, absolute value of x plus 2. So notice the plus 2 was happening on the outside. It wasn't happening to the x. So therefore, it's affecting the y values. So every graph on the parent function that you know from 1.3, I guess, is you would take every point and you would just add 2 to the y values, and that would get you this new graph. Same thing right here. If we had the minus d, that's going to move it down d units because of the fact that it is on the outside. If I make up that same graph, it'd be the absolute value of x minus 5. And so that would move it down 5. And notice again, I know that because it's on the outside. Every point on the parent, I could just subtract 5 from that y value, and that would get me the new points on the new graph that was shifted down 5. And that's right there is what we got when we move stuff, when we translate it left and right or up and down. So those are your slides, your translations, right? Those are your slides. Now we're going to talk about if somebody tries to multiply or divide the x. Those are your stretches, your strengths, and your reflections. So let's talk about, the first one we got here. Somebody multiplies the inside with the letter B. So that would then tell me I got to do something weird here, right? If it's inside, it's always horizontal. Always, if it's inside, it's horizontal. But you have to do something weird. So since B is a number, we're saying it's bigger than 1. Since B is a number bigger than 1, it's actually a compression, which that feels weird. It's a horizontal compression of 1 over B. So what would that look like? That would look like y equals, and then now I'm going to go on the inside, so I'm going to do it inside the absolute value of bars. Let's do 4x, right? So if I do that, that is actually a horizontal compression of 1/4. So what does that mean? That means you take every point on the graph that you knew, the parent graph, and all you'd have to do is multiply them by 1/4, or I guess in this case, I will say I'll do 1/4 times every x, and that'll get you the y value. And so that right there will get you your horizontal compression. Even though you look at the problem, see that 4 there, but because it's with the x, it's something weird. What about here? Then if I multiply by a fraction, then all that means is it's a horizontal because it's on the inside. It's a stretch, though, of b. It's multiplying it by b. So that would look like something like, let's do 1/7. So I'll have 1/7 of an x, or x over 7, or something like that. That would be a horizontal stretch of 7. So it's 7 times stretched horizontally. Every point that you had would then be multiplied by 7, and that would be your new point. So that whatever that b value is, that's what you would multiply by. That's your horizontals. Then of course we got verticals. So they're kind of nice. They're on the outside. So these are your vertical, and now this is kind of nice because this would be a vertical stretch of a, because a was bigger than 1. So again, nothing weird there on the outside. Vertical stretch of a. So say we have y equals 4 absolute value x, right? That would be a vertical stretch of 4. So every xy point that you had, all you're going to do is multiply them y values by 4, and you got it. All right, now you're probably getting the hang of it. This would also be a vertical, but now it's going to be a compression because it's smaller than 1. So a vertical compression of 1 over a. So we use 7, so it would be 1/7 absolute value of x. Oops, forgot the y. So that is a vertical compression of 1/7. So every point xy would now have their y values multiplied by 1/7, and that way they would be compressed. And then the last two on the stretches are actually reflections, right? So if you see that somebody went through and changed the sign on the x's, that just reflects it over the y-axis. And so every point that you had, all you would have to do is put a negative on the x. And if they put the negative out front, that reflects it over the x-axis. And all you have to do there is change the sign on the y values. And there's your breakdown of these things. Now, what's super important, you got to be able to recognize which ones are stretches, which ones are compressions, which ones are translations left and right and up and down, right? So if they're multiplying, it's stretching and compressing. If it's inside, it's horizontal. Outside, it's vertical. If same thing with adding and subtracting. If it's inside with the x, that's a horizontal translation, left or right. Again, doing opposites if it's inside. And if it's on the outside, that's your up and down. Super crucial to recognize all these translations. And I'll show you why. Here's just a fun little problem that we can do now. Is that I have some I have some graph here that is some function. I don't know what it's defined as, but here it is, and you can see all the points. And in fact, I'm going to go through and I'm going to pull out all the xy points of this graph. So here it is. So you'll notice we have -2, what is that, 4? -2, 4. We have 0, 3. We have 1, 0. And we have, what is that, 1, 2, 3, 4, -1. So there's our graph, right? Now that defines the function. But look what we want to do. We want to move it right 3, and we want to move it up 2. So what that means is, first of all, I want to make sure there's no stretches, which there isn't, because they would be first. And then I'll do my slides, and these are both slides. So in other words, I'm going to take every x, and I'm going to move it right 3, which means I'm going to add 3. And I'm going to take every y, and I'm going to add 2. Now notice when I did this, I did the opposite for the x, but I did the copying of the y. So that's why, again, the x's are the tricky one. But it's true for every graph, all 12 graphs that we did. So now you can add 3. So you add 3, you get what? 1. You add 2, you get 6. So the point 1, 6 is on the graph. Now I take 0, 3. I'm going to add 3 to it. So 3. I'm going to add 2 to it is 5. So 3, 5 is on the graph. 3, 2, 4, 5. Then 1, 0 is going to get turned into 4, 2. So 4, 2. And then last but not least, 4, -1 is going to turn into 7, 1. And I'm going to graph that 4, 5, 6, 7, 1. And now if I connect these, it should look like the graph was translated right 3 and up 2. And it does. That looks like it's right 3 up 2. So I am feeling great, right? So let's go ahead and try the next one. We got the exact same points. So here I am going to make my XY chart. And I'm going to copy it down here. So it was -2, 4, 0, 3, and 1, 0, and 4, -1. And I want to, oh, look at that. We have a flip on the outside, so that's over the x-axis. So this is a flip over the x-axis. And we also have, or you can call it a reflection over the x-axis. And inside with the x, we have a multiplier of 1/2. So it's inside, that means a horizontal stretch of 2. So this has a horizontal stretch of 2. Now remember, we're going to do our multipliers first, but in this case it's kind of nice because they're both multipliers. We're going to have to multiply these things. So when we multiply, if you look up, we have a horizontal stretch of 2. That means all the x's need to get doubled. So get doubled. And then to reflect it over the x-axis, I need to change the sign on the y's. And so now if you look at our original points, you'll get -4, -4 is on there. You'll get 0, -3. You will get 2, -0, so I guess that won't matter. And last but not least, I get 8, 1. And now let me show you what it looks like when I plot those points. It should look like it was flipped over the x-axis and horizontally stretched. So -4, 1, 2, 3, 4, 1, 2, 3, 4. There's -4, -4. 0, -3. 2, 0. And 8. I think that's all the way to the end. 8, 1. And now that, as I draw it in, should look like I took the graph and I not only horizontally, left and right, stretched it, I also flipped it over. And you can see it looks like it was stretched by a factor of 2, and it looks like it was flipped over. So there you go. Those are all the things that you're looking to do. I'm going to ask you a question, and then we'll come back and talk about this some more. Great job on the transformations. And then you can see there I did number 3. So if you want to go ahead and do that, or kind of pause the video and then do it, and then you want to check your work, do it. It had some neat stuff in it. It did have a horizontal compression and a left 3. So just make sure you stretch before you slide, but it kind of happens naturally. Multiplying the x's by a half you had to do first before you could subtract the 3. So here's my compound of both of those. And then you can see I got each point and I graphed it, and it does look like it's shifted over to the left 3 and horizontally compressed, so it's a little skinnier. Now let's talk about 2 that get missed a lot, square root graphs, because people don't factor out the 3. So if you look at this first problem A here, a lot of kids will think it's right 6 when they look at it at the first glance, and that's like, oh, that's the thing we got to be worried about. You want to make sure that whenever you talk translations that you have x by himself. So he's got to be linear. We are not linear, but he's got to have a coefficient of 1. And so I got to factor out that 3. Ooh, did a horrible job of factoring right there. Make sure you factor out that 3 and you actually get the right thing, is that you get x minus 2. Why is that important? Because now you can see that that is a right 2 shift. So it's a right 2 shift, or rights 2. And the 3 I can also see there is inside, so it's a horizontal. It's bigger than 1, so that's a compression of 1/3. So I'm going to say a horizontal compression of 1/3. So all that tells me is what I'm going to do. Remember, on a parent function, if you have the parent function points, then all I would have to do is, if I'm going to do a horizontal compression of 1/3, I'm going to multiply the x's by 1/3. And then to move it right 3, I'm going to have to add 2 to that, and we can just leave the y's alone. So remember our square root graph. Our square root graph had some important points on it. It had the points 0, 0, and remember 0, 0, so I'll put like 0, 0. And then remember we had 1, 1. And then remember we had 4, 2. And that was your square root graph. That's enough to get you a square root graph. You could plot more if you wanted to. But now do these transformations, right, that we've noticed from reading the problem. We know what it is, and now let's apply them. So if I apply it to the first point, I get the point 2, 0. If I apply it to 1, 1, I get 2 1/3, comma 1. And if I apply it to the last one, I get 3 1/3, comma 2. So what do these points look like? Well, where's 2, 0? So 2, 0 is right here. And then 2 1/3, comma 1 is right there. And then 3 1/3, comma 2 is right there. And you can see that this graph is going like this now. It's a lot steeper. And why is that? Because it was horizontally compressed by 1/3, and it was also shifted right 2 units. So the blue graph is the correct graph. I just wanted you to see the transformation. Tricky, tricky stuff, right? All right, look at B, the other mistake. People don't always factor out like the 3 in that one. A lot of times people will forget to factor out the negative in front of the x. So the first way you want to read this graph is a log 3 graph of negative x plus 5, if I just write it in the correct order. But then notice that negative in front of the x. That's no good. So I need to change that to a negative 1 x minus 5. So you can see that you would have been you could be completely tricked by what the transformations are on this problem. So the one things I notice is that this is right 5, and it's also multiplying to the x. We're having a flip on the x. So therefore, this is going to be, it's on the inside, so this is going to be a y-axis reflection. So this is a y-axis reflection. All right, so what does that mean? That means you got to change the sign on the x and leave the y alone. And right 5 means that you got to add 5 to all the y's, or to all the x's. So therefore, what do? You take every point that you have, and you translate it by changing the sign on the x and then adding 5 to it. So that's what we're going to have to do for this problem. So what are our magic points of a logarithm? Well, the cool thing about a logarithm has a vertical asymptote at x equals 0. So we're going to have to move that guy. And he has the point 1, 0 and the base comma 1. So in this case, 3, comma 1. Those are just points you want to know. So here is the original one. I guess I'll do it in this red. So here it is, right? And then I'm going to have to plot 1, 0 and 3, 1, 1, 2, 3, 1. The graph would look something like this of a logarithm, right? And then it shoots out this way. So that's your log graph. All right, let's do our translations on it. So the first thing we want to do is a sign change, and then we want to add 5. So, oh, and I forgot the comma y there. That's a little crazy. So if I do the sign change, -1, 5 is 4, comma 0. So our first point is going to be 4, comma 0. 1, 2, 3, 4, comma 0. And then our second point, sign change, would be -3 plus 5 is 2, comma 1. So 2, comma 1 is our next point. 1, 2, comma 1. And I forgot to do my vertical asymptote, which would get a sign change on that 0 is -0, and then add 5, such as x equals 5. So here's 5 right here. And now remember, this thing will start at the bottom. It'll start very close to the asymptote, and then it'll go through those 2 points and out of here. And so just because we know few things about the log graph, like its vertical asymptote, like a 0.10 and then the point base comma 1, that's enough info that we can just do the translations, graph it the other way, and be finished and not have to be scared of any graphs at all. And the only last thing to worry about is what does absolute value do? And so if you read that little blurb right there, you'll see that if you have absolute values around the whole function, then anything below the x-axis will flip over to be above the x-axis. And the other one, if you have absolute values just around your x, then anything on the left side would now be reflected to the right side. And so that is all you have to know there, and we can talk about that one in class. Have a great day and stay happy.